The next law that we're going to deal with is called Amperes' law. And the APC objective specifically is this. You've got to be able to use Amperes' law in symmetry arguments with the right-hand rule to relate the magnetic field to the current for planar and cylindrical symmetries. We've got to be able to figure out the magnetic field due to a cylinder of current, i.e. a wire, or a plane of current, which is like a flat conducting plane where current's going all the way through it, through the entire plane. So this is what we got to use Amperes' law for only these two situations. You will see that it's way easier than the Biot-Savart law. So here is Amperes' law. It's the integral, and it's an integral over a closed loop. That's what that means right there. It's through a closed path. It's a line integral. The integral of b dotted on the little arc length ds will be mu naught, again our constant 4 pi times 10 to the negative 7, times the current that is puncturing that loop. The current that is puncturing the loop. And you'll see why I use the term puncturing. Okay, so this becomes very easy for certain types of situations. So let's take this situation right here. What I've got is I want to figure out the magnetic field at a distance r from this current I. Now this loop, this is just what we call an Amperian loop, similar to a Gaussian surface. There doesn't have to be anything out here. You do not need a wire. You don't need anything here. This is just a loop that we are just geometrically constructing in space. So what this law means is that if you take the magnetic field at this point right here and you multiply it by that little tiny arc length ds, and then you add it to the magnetic field right here multiplied by that ds, and then adding the magnetic field times ds, and the reason the dot product is cosine, we are only getting the parts that are parallel with our geometric loop, and it turns out the magnetic field is got to be parallel with this loop all the way around. So that makes it nice and easy. Just like Gauss's law, integration has to be very easy or it's not going to help. So these are all the b's times the ds's. You add them all up. They will, when you integrate that, add all up the b's times these little ds's, you will get mu naught times I, where I is the current puncturing any surface that is formed by this loop. Any surface. Now there's the simplest surface. It's just a flat surface that's created by that Amperian loop, but it is true for any surface. In fact, if this were just the rim of a balloon, you could have this surface right there is also bounded by that loop. It still works for that surface. Here's the easiest surface that's bounded by that loop. It's just like that flat surface. So that's why I say that this current is puncturing this surface right here. It's going through any surface bounded by that loop. Now, when we actually do this integral, this is why it's easy. B dot ds, B is always parallel to ds. All these ds vectors are like that. The magnetic field is always going to be parallel to those. So what is the angle between B and ds for this whole loop? What's the angle between B, the magnetic field? Use your right-hand rule to figure out the direction of B. So we got thumb going up. This is in this picture, the current is up. So use your right-hand rule. It curls around in a circle. And notice that B is always exactly parallel to every part of that loop. So what is the angle between B and any one of these little ds vectors? It's 0, so our cosine of 0 gives us 1. So this becomes, B dot ds just becomes B times ds integral. And then because we are by symmetry, this r is the same for every point on this whole loop. It's the same r, so that means that b is a constant because r is a constant. That can come out of the integral. And then all we got to do is integrate ds. That's all we got to integrate. But that's easy. The distance around a closed loop of radius r is what? 2 pi r. So that's why this is so easy. We get, again, we get the integral of b ds equals mu naught I. So here's, let me go ahead and do this on another page. If the integral of b dotted on ds is equal to mu naught I, where I is the current puncturing this thing, this, because the magnetic field around that loop is constant, bring that out. You get integral of ds. Notice that because they're parallel, we cosine of 0 is 1. We lose the dot product. And then this is mu naught I. So all you got to do is integrate ds, gives you 2 pi r. And then just like Gauss's law, it's as simple as this. Magnetic field at that point is mu naught I over 2 pi r. That is what I already gave you as just a given equation, but that's how you derive it using Ampere's law. The magnetic field is mu naught I over 2 pi r, where r is the distance away from the wire. So this is the magnetic field due to a wire carrying current I.